you cannot improve the tracking. Let's say, if you want to improve the tracking, and say, I want a better tracking. But what is a better tracking? You need to define what is a better tracking. To understand what is a better tracking, you need to understand what makes the tracking. What are the parameters that create the tracking? And for that reason, we split the tracking into what we call variables. And we analyze those variables separately in order to see which one is the bottleneck, or which one is meeting our expectation and which one is not, in order to make progress on the ones that are weak, and not degrade the ones that are good. Because it's very easy to improve something if you have the freedom to degrade everything else. Here the goal is not to degrade everything else, it's to keep the level we have on the good one and to improve the bad one. So when we look at the first one, which is the resolution, so we call it CPI because it's count per inch, but users call it DPI because it's dot per inch. Dot per inch means on the screen it's a dot, but for us in the sensor it's a count. So that's the difference, but it's the same. It's the same item.
I'm sorry, what's the CPI for?
CPI is count per inch.
Count.
Count. Because the sensor report counts, but the display dots. That's the reason of CPI and DPI. So just let's talk about the resolution. The resolution, how the resolution is built. If you look on the sensor from the side and you cut the sensor, you will see something like this. You will see the sensor, and in the sensor there will be a matrix area here, where you have pixels. And this, you will have a lens, and then you will have the surface here. And what happens is that your pixel will be imaged on the surface, and it will build a pixel on the surface in a way. And what we say when you say count per inch is how many those pixels we can put in 1 inch. This is the resolution of the system. And this is the optical resolution of the system, because the system has a size here that is fixed. It has an optical lens that gives a given magnification. It's the optical formula, and it builds a pixel size on the table. And this is the minimum item the system can see natively. And then you will have, for every those pixels, you will have an image, and if you move by 1 inch, you will know how many native pixels you have. And this is the native resolution. And believe me, the native resolution is much lower than every resolution you see on the products, because it's impossible to build a sensor that has 8000 dpi native. It will mean that you will have an imager that is barely that big, and a system that is barely that high. So it's not possible. So how can we build higher DPI? We can build higher DPI by subdividing the pixels. So if you look at, again, if we look it from the front, we see this is the matrix of pixels. What we can do, we can subdivide. So each pixel, we cut it in 2. So in that sense, we double the resolution. And then again, you can double it again by cut it by 2, and so on, and so and so. By doing that, you are going away from the native resolution, the optical resolution, but you are improving the sensitivity of the system. The problem is that the drawback is that you are raising the noise floor, because the pixel has a given sensitivity. If you split it by 4, it has much less sensitivity, because it remains much less signal to noise capability. And then at a point you reach a level where your pixel has not enough information to give a reliable tracking. And then that's the reason why raising the DPI is completely against the logic of performance in a sense. It's okay if you cut it by 2 or so, but if you start to raise the DPI by a lot, just because you want to have a big number on the box, then you end with a product with a lot of DPI, but it's just unusable. It's very nervous. It has a lot of noise. It is not capable of follow tracking on some surfaces, because the less pixel area you have for one dot, the less efficiency you have, so the less capability you have to follow the tracking on a difficult surface. And this is just to explain you a little bit about how the DPI and the resolution are calculated and are created. And again, it's not like a scanner. It doesn't mean that if you have 8000 DPI, you have the capability to see more information than a system that has 800 DPI. It's just you have cut the area in a smaller slice. It's just this. So it doesn't make your system less good. It's just a relationship between your hand movement and your screen movement. So in fact, DPI is a translation between how many pixels I travel when I move my hand by 1 inch. It's only this. It's not a question of any kind of quality of tracking. It's just a relationship, a magnification or a translation factor. Any question on this first? So the next point is angle error. And here there are 3 kinds of angle error. And again, I go here. Admitting I want to move from here to here. So this is A and this is B. The ideal system will do this. This is, okay, admitting it's a straight, not that good, but okay. The reality, you might have something that is, so first you might have something like this. And here we have what we call the unbiased angle error. So it means that at the end, you have an angle error, because instead of arriving here, you arrive here. So this is what we call the unbiased angle error. This is the angle error that is generated, that is systematic. And then around this angle error, we have what we call the 3 sigma angle error, which is the variation. So the local variation of this angle error. And again, the user can very cope with the unbiased angle error as long as the angle error remains low. Because naturally you will correct. It's natural. You will do it, you will even not feel it, you will do it. But the 3 sigma, you will never bar with it. Because 3 sigma is unpredicted. So it's a variation around an error. So you cannot predict something that you don't know. And this is the most critical one in terms of angle error, because this one is very, very difficult for the user to cope with. So we have to work very good to improve this parameter. And then there is the last one, what I call angle snapping, because there is a function that was implemented in the sensors at the time of Office, where you can imagine this is the orthogonal. The function that was implemented, it was to help user to do straight lines. And the function was simply doing this. It was creating a cone where when you are inside this cone, whatever you are inside this cone, the system only reports straight. So it's only straight. So if you are here, your position is moved there. And this is maybe useful for Office, for graphic people that are doing straight lines, or CAD people who are doing PCBs, but it's really a nightmare for gamers, because when you are a gamer, what you want to have the raw motion from the sensor, you want to feel really your hand movement. If you are doing a small arc of circle, you want to see all the points. You don't want to have, because at the extreme, if you do a circle, admitting it's wrong, if you have snapping, you will see this. You will see a circle with square here, because as long when you come close to the vertical or the horizontal, the system will report straight. And then you will have a circle that looks like a square with rounded angles. And this is very bad in terms of tracking quality. Okay, so those are the aspects of angle error. Any question? Okay. So then there is what we call resolution versus speed error. Resolution versus speed error, for me, it's really sensor accuracy and repeatability. What does it mean? It means if I take my mouse on the table and I move it very precisely from one position to the other one, I cover always the same distance, let's say 20 centimeters. I do 20 centimeters, I do it at a low speed, and I do it at a fast speed. I should normally see on the screen always the same displacement if my system is accurate. And believe me again, there are differences. And this is one point where the sensors are not equal. And here, the user, by the way, they call it sensor acceleration. It's not sensor acceleration. It's a sort of misinterpretation of the sensor with respect to the speed. So the sensor doesn't have the ability to see the same number of count if you move it slowly than if you move it quick. And here we worked a lot to improve that point for gaming sensor, because we know that gamers, especially FPS gamers who want to do headshots, and they want to do a system that is precise. They know there are one that is coming here and another one that is coming there, and when they do this movement, they come exactly at the right position to shoot both guys. If you have a bad mouse, then you will overshoot. You will end somewhere apart, or before if you undershoot, but whatever, it is, you will have problem with this parameter here, what we call resolution versus speed error. So this is an aspect we try to look at. And then there is another one that is evil as well, it's the ripple. What we call ripple, users call it jitter. We split it in low frequency and high frequency, and here again, if I do the ideal line, and if I do what's happened in the reality, I can have something like that. And the ripple is the variation around the ideal trajectory I have. On this, if it's low like that, it's low frequency. And I could have something that is like that, around it, which is a high frequency. It means you have a cursor that is very narrow. On this, we try to minimize it. And this is clearly coming from that. The more you raise the DPI, the more you have this problem. Because it's natural. You have a problem with the noise floor, you have less dynamic, you have less capability of the sensor to identify what is real motion and what is wrong motion, and your system is hesitating. And sometimes it believes, okay, it's tracking, no, yes, no, and then it creates this variation, because the ideal trajectory is there and is capable of seeing it. But if you ask too much DPI, you will end up with something like this, very nervous and very unpredictable. So this is what we call ripple. Any question on it? No. Okay. And then dropouts. This is the most easy to explain. There is no DPI. So it means that the surface is not giving any kind of information to the sensor for tracking. So the sensor is lost and you report nothing. So it means you are moving your hand and suddenly your cursor is stopped and then it restarts and it starts and restarts. And this is what we call dropouts. So this is evil as well, because for gamer, for sure, but even for office user, because you cannot work at your office trying to move in your Word document or whatever, and your cursor is doing a sort of go, no go when you prefer. So this is something that is very important to understand, but this is easy to solve. And then we have what we call pixel walk, which is the low speed accuracy. So it means that when you are moving your sensor or your mouse at a very low speed, you reach a speed where the system is hesitating between motion or not motion. And if you move it so slow, you have what we call a starting speed. And if you move it close to the starting speed, then you arrive in a situation where your system is hesitating as well. And the goal is really to minimize, to make the system capable of tracking even at a very low speed. Because the user, often when he moves at low speed, it's because he wants to do something very accurate. And he wants to grab something that is maybe 2 or 3 pixels away from his position. And if the system is not capable to react well and to move those 2 or 3 pixels, but he moves by 5 or 6, then you overshoot. And then you go back and then it undershoot. And it's a nightmare. It's a nightmare. Sorry. So the pixel walk is a point when you want to have something precise, accurate, and you want to do precise and accurate work. You need to have this mastered as well. And then the last one is what we call circle drift. And here, the most easiest way to rate the quality of tracking is to do a circle. Because why? If you do a circle, you do all the angles, because there are all the angles in a circle. So if you are capable of doing a circle, and if you start from here and you close at the same location, then it's not bad. Really, it's not bad. Especially if you do the circle at different speed and you always end with a very good circle, then it's not bad. The problem is that if you have problem with the timing, let's say, if you start here and you send motion for one circle to the machine, but you end here, it means you end here, it means that your system was not able to start at the right time, and then it missed the departure, and then at the end, it could not close the circle. And this with the circle, because with all the other one, we are capable of rating the capability of tracking at many angles, but with the circle, we use the circle mainly for the timing aspect, to see if the system is capable of wake up directly and report the whole circle. So, and by the way, if your system is bad like that, then when you do the second circle you have an offset, and then the third circle you have another offset. What does it mean? It means on your screen the user will feel that the cursor is going away, so you have to recenter, because you have something that shifts your position apart, and this is not what we want. Any question on that?
All clear.
All clear. Perfect. So you can welcome to work at Logitech. Okay, so this was for the theory of the sensor. So the aspect of tracking on what's important to